Hello, my name is Celso. I am a PhD student under Professor Jumao, and I'm here today to present our project that's entitled Non-Contact Bridge Assessment via Computer Vision and Artificial Intelligence. I hope you all enjoy. So, starting with the motivation, why do you want to use cameras instead of the traditional sensing techniques that we currently have available? The first one that comes to mind is about the portability of this new system. So while we need several hours to actually prepare the test and equipment for a strain gauge or an accelerometer test, for the camera based, we can only find a good place, place the camera and record the bridge, and then we'll have everything set. Also, it is low cost since we don't need a dedicated system only for one bridge, and it allows to do a fast setup without interrupting the traffic since it's just putting somewhere on the side of the bridge and recording the data. And finally, since the camera acquires a huge, very large amount of pixels, each pixel contains dynamic information of our structure. It can extract full field information. But how can we extract those information from images? So we basically used two algorithms here. One is the phase-based motion extraction and the other is phase-based motion magnification. Both of them works in a similar way, but quite differently. The phase-based motion extraction convolutes each frame with the Weber wavelet, generating a phase that amplifies the motion and then allows us to extract subpixel motion. With that, we can extract a displacement of the order of 1 or 2 millimeters, even though we are extracting a video from a bridge that's 20 meters away from us. So since the frames are many images taken over time, we can extract the position of a part of the region of our interest and then track this motion over time. Then simply applying a Fourier transform, we can extract the natural frequency of the bridge. Similarly, for phase-based motion magnification, once we convolute those frames with the Gabor wavelets, we can get this phase and this phase of the frame, and this phase actually contains the position information of my structure. So if I bandpass filter this frame at this specific natural frequency and then multiply by a beta factor, then I can amplify the motion of only this mode shape of my interest. And with that, I can reconstruct the video and see then the bridge, for example, its first bending mode shape, but now with a very big motion at the point that we can actually see on the video the mode shape of the bridge. So using those algorithms, we did some laboratory scale bridge tests as a preliminary data set for our data-driven algorithm. So we did this on a laboratory scale since we can control the input and also simulate damage with the bridge. As we can see here on the figures, we actually are able to extract the natural frequencies and the mode shapes of the bridge for each case, and also we can observe that there is a shift on the natural frequency, and then there is also a change on the mode shape, which we later used as input for our machine learning algorithm to detect damage. We also did two tests on real bridges, one of them located in Lowell, Massachusetts, and the other one, the Gristmill Bridge, located in Hampton, Maine, in order to compare the phase-based motion extraction and phase-based motion magnification with other softwares that use camera-based sensing techniques and with traditional sensing techniques to see how accurate is our system. So on the graphs on the left, we can actually see that there is a good correlation on the natural frequency extracted both by the RDI systems and with phase-based motion extraction. And on the graphs on the right, we can see that we can actually extract the excitation from the truck on the Gristmill Bridge. And with that, we can accurately predict when the truck is passing and extract its natural frequency on the forced vibration, free vibration, or even with only ambient vibration. We also got a very good correlation between the strain gauges that were installed on the bridge and with the phase-based motion estimation. So with that, this data set can be used in the future for possible damage detection using either a machine learning algorithm or an outlier detection algorithm. As I mentioned before, we use these data extracted from the laboratory scale bridge to develop a data-driven or machine learning algorithm that could actually predict damage in the structure. So for that, we basically combined two different neural network algorithms in order to extract the features from the frames and then extract the behavior of these frames in order to detect damage. So we used both convolutional neural networks and long short-term memory networks for that. We used convolutional neural network for its great capability of feature learning. Basically, it convolutes the frames with many different kernels and tries to extract patterns between them. Then we can group those packages of patterns from frames and use as input for the LSTM, which then will try to predict a change in the time domain of those patterns. And then you can actually use the output from the LSTM on the neural network. It then can predict if this package of frames belongs to a health or a damaged video. So for that, we basically extracted the motion of the bridge after applying phase-based motion magnification. So we don't see the background. And we also selected the regions that we cannot see the damage so that we really extract if the structure is damaged or not based only on the natural frequency and the mode shape. As we can see here on this confusion matrix, we were actually able to extract a very good result with above 90% of accuracy for those preliminary results, which shows a good potential to, in the future, use real bridge data and then extract if this bridge has any sort of changing of its behavior due to either damage or some other factor that can be further investigated. So in conclusion, we can see that non-contact sensing with video cameras, it's a very good, portable, and fast bridge evaluation technology, since we don't spend much time preparing and we don't need to stop the traffic to do our testing. Phase-based motion extraction also proved to have a good accuracy when we compare it to other camera-based sensing techniques and even with traditional sensing techniques. In addition, phase-based motion magnification is actually able to amplify the motion of the mode shapes, allowing a full field dynamic identification, which increases the feasibility of machine learning or any data-driven algorithm to predict any type of damage. And finally, the deep learning algorithm demonstrated extraordinary capability for damage detection when processing video-based data camera. So finally, I would like to thank my advisor, Professor Jumao, and my lab mates at UMass Lowell, and also for the Transportation Frustration and Durability Center at UMass for funding this research. And also thanks to everyone who watched this presentation. Thank you.